Okay, this is part 3 of the magnetism lecture. Okay, make sure that you take a look at my short demonstration video, Magnetic Forces upon a Moving and Charged Particle, prior to taking a look at part 3 of this lecture. Okay, so in this portion of today's lecture, we are going to be wrestling with the following expression. F equals QV cross B, where Q is an electric charge, it has a velocity vector V, and it's in a region of space where a magnetic field is present. We want to describe the subsequent motion that occurs for a couple of situations. Okay, so the first situation is the first of the lecture examples for this lecture. So make sure that you copy down the following problem. A proton with a velocity V is introduced into a region with a constant magnetic field that is perpendicular to the velocity. Describe the subsequent motion, and then repeat for an electron. Okay, so let's say right here is a proton. The proton has a charge E positive like so, and it has a velocity vector V in this region of space where a magnetic field is present. Okay, let's say that by definition the magnetic field is into the board like so, and it's uniform. Okay, now if we do F equals QV cross B, we'll then do the cross product by using the right-hand rule. We'll have QV in this direction like so, cross B into the board, then gives us a force vector that is upwards on the diagram. Like so. The question is, however, is what then subsequent motion occurs? Well, if the force vector is perpendicular to the velocity vector, then the force vector does not change the magnitude of the velocity vector, but it does change its direction. So let's say, for example, that a short time interval, delta t, goes by. Like so. So then a moment later, basically, we'll have the following situation. Okay, here's now the velocity vector of the object, of the proton, like so. And then once again, we have the magnetic field here into the board. So we've changed the velocity vector by a delta V vector, if you will, which points upwards on the diagram in the same direction as the force vector, in the same direction as the acceleration. So I'm not drawing the delta V vector here on the diagram, however. Okay, now watch what happens when you do the cross product again. You have QV cross B, then gives you a force vector that is like so. So the force vector, in other words, doesn't always point upwards on this diagram, but it's always perpendicular to both the velocity and the magnetic field vectors. So if the force vector is always perpendicular to the velocity vector, what then motion occurs? Well, it's uniform circular motion. So what that then means is that the proton circulates on this diagram here in a counterclockwise fashion. That is, the subsequent motion looks like this. Like so, where right here when we started the problem, here is our proton like so, moving with a velocity vector V in this direction, the magnitude of which is just V. Okay, there's going to be a radius associated with this circle R, and there's also going to be a period associated with the motion. Usually what we do is we just derive an expression or two that describes the radius and also describes the period. So here's how we're going to do that. We'll just do a little bit of F equals ma here. Except now in this case, the acceleration is the centripetal acceleration inwards towards the center of the circle. So the left-hand side of the expression comes from the cross product from a few minutes ago, QV cross B. The magnitude of that force, however, is just the charge of the proton, multiplied by V multiplied by B. So this is just QVB times the sine of 90 degrees. There was a 90-degree angle between the velocity vector and the magnetic field vector. Sine of 90 degrees is equal to 1. So it's basically just QVB. Okay, this then equals mass times acceleration, mv squared over r, like so. And then we can go ahead and replace the speed v here with 2 pi r divided by the period. The m here, by the way, is the mass of the proton. Let me make a note of that here. So commonly on the actual AP exam, you'll be asked to describe the subsequent motion for this situation. It's uniform circular motion, and then derive an expression involving the period and or the radius, which ultimately just comes from these expressions here. Other than that, typically what you're going to see is some sort of plug and chug situation. Okay, now let's repeat then for an electron. So let me label this once again here as a proton. And then on the lower board here, now let's see what happens for an electron. Okay, keep in mind that the electron has a negative charge associated with it. We'll label it as E minus, and then once again, let's say that the velocity vector V initially points in this direction like so. Okay, and then into the board once again is the magnetic field B. Okay, now if you do QV cross B once again, you're going to get a force vector upwards. However, remember that the charge of the electron is negative. So then therefore the negative sign takes the direction of the force vector, the direction of my thumb, and it reverses it into the opposite direction. So then therefore here on this diagram, the force vector therefore is downwards here initially. Like so, or once again the magnetic field here is into the board. So you end up with uniform circular motion once again, but in this case the circulation is in a clockwise fashion. It would be like below that circle, if you will, on the diagram above when talking about the proton. So the electron would basically circulate like this on the diagram like so. So right here is the electron when we start this process. Here's the magnitude of the velocity vector V. Right here is the center of the circle. And then right here is the radius. And then you would once again have the subsequent equations there to describe the motion. Keep in mind, however, that even though the charge of the electron and the proton is the same value, the mass of the electron is considerably less than the mass of the proton. So then therefore the parameters here involving the radius and the period, they're not going to be the same for the two different types of charges. Okay? Okay, so that completes that problem. Let's go ahead and move on to the next problem, which is the last problem of the lecture. Okay, go ahead and copy that problem down into your notes. Pause if you need to. I'm going to go ahead and erase the board here. Okay, and then here is the situation. Okay, specifically it's going to be an electron which is negatively charged. And it's introduced into the following region. There's a diagram I'll draw on the board here in just a moment, where the magnetic field is constant and in the z direction. Okay, the initial velocity of the electron is the following: v sub y j hat plus v sub z k hat, describe the subsequent motion. And then there's a diagram provided which looks like this. All right, so right here is the magnetic field, like so, in the z direction. And then here is the xy plane like so. And then at this moment, the electron is right here along the x-axis, and it has a velocity vector v which looks like this on the diagram. Okay, now there are components associated with that velocity vector. Right here and right here, where right here is the velocity in the y direction, v sub y. And then right here is the velocity in the z direction, v sub z, okay? Okay, now let's go ahead and actually do a cross product here as the determinant of a matrix to determine the direction of the force vector that's going to be exerted upon the electron. So I'm going to go ahead and do QV cross B. Oops, QV, excuse me. There we go. Cross B. Okay, now yeah, the charge of the electron is negative. That will then reverse the direction of the force vector once I calculate it, but let's go ahead and find the direction of the force vector here by setting up the determinant of a 3x3 matrix. All right, so that force is going to equal the charge of the electron multiplied then by the following. So first of all, V, like so, and then cross it into B, like so. And then we'll once again calculate here a determinant. Okay, so recall how you do, in fact, calculate the direction of a determinant. Okay, first of all, in the I hat direction, we'll have v sub y times b, and then minus 0. Like so. Okay, and then for the j hat direction, then we're going to have 0 minus 0, which cancels out. And then also for the k hat direction, we're going to have 0 minus 0, which also cancels out. So we end up with this expression here. Initially, it looks like that the force vector is in the positive x direction, that is like so, but keep in mind that the charge of the electron is negative. That then reverses the direction of the force vector once again, so then therefore the force vector in this diagram like so points in the negative x direction. Okay, so then what happens in terms of the subsequent motion? Well, basically there are two types of motions that occur here, one of which is identical to the previous example, that is the uniform circular motion. The uniform circular motion takes place in the XY plane. Okay, now the magnitude of the force itself is this quantity right here. And this would then equal mass times acceleration in the XY plane. Okay, the acceleration in the XY plane is the centripetal acceleration. The constant speed of the uniform circular motion would be the component of the velocity vector v sub y. This guy right here doesn't change, and the reason for that is because the force vector is always perpendicular to that component of the velocity vector. So v sub y never changes. So then therefore F equals ma is going to be written like so. This right here is the mass of the electron times the speed squared and then divided by the radius of the circle. The radius of the circle, once again, is in terms of the xy plane. But we also have right here this component of the initial velocity vector v sub z. Notice that the force vector is also perpendicular to v sub z. So then therefore the force vector itself actually has no effect on v sub z whatsoever. V sub z remains a constant. So then therefore you have the combination of two types of motion. You have a uniform circular motion that occurs in the xy plane, and you also have motion in the z direction where v sub z is equal to a constant. So can you trace out then therefore for me exactly what the motion of the electron looks like? Well, the electron spirals along the magnetic field line. It looks like this. So once again, here's the xy plane like so, and then here's the z direction, combining it in the magnetic field lines like so. So combining the two types of motion together, you then end up with something that looks like this. Like so, and so on. So the electron then, the charged particle, it spirals along the magnetic field line. Okay, now this distance right here on the diagram, this distance right here is given a name. It's referred to as the pitch. That distance is speed times time. It's equal to the speed, however, in the z direction, the component of the initial velocity vector v sub z, and then multiplied by the time from here to here. Now I've drawn the diagram such that the time from here to here corresponds to the period of the uniform circular motion which takes place in the xy plane. So the pitch, this distance right here, is equal to the speed in the z direction and then multiplied by the period of the uniform circular motion in the xy plane. So suffice it to say, a charged particle then spirals along a magnetic field line. There are all sorts of implications associated with this and applications of this situation, particularly in astronomy. Let me just go ahead and conclude the lecture by giving you a qualitative understanding of one of those applications, and that is the Aurora Borealis. Okay, let's say that right here is the Earth, like so. Here's the Earth's equator, north and south poles. And as I have already previously described, the Earth's magnetic field is a dipole shape. However, when the Earth's magnetic field interacts with the solar wind, which is a stream of charged particles coming off the sun, the net effect of this, the net magnetic field then, which then results, is still of a dipole shape, but the magnetic field of the Earth kind of flares out in this direction like so a little bit. This is sometimes referred to as a magnetic tail. So it kind of more or less looks something like this. It kind kind of flares a little bit more in this direction, away from the sun, due to the interaction of the Earth's magnetic field with the solar wind. So let's say right over here is the sun, and then here's the solar wind. So the solar wind is basically a stream of charged particles coming off the sun. Those charged particles, by and large, consist of single electrons and single protons, also some ionized helium as well. At any rate, however, basically what the Earth's magnetic field does is it protects us from the mercy, if you will, of the solar wind. So it deflects the solar wind away from the Earth's atmosphere. This then means that the Earth's atmosphere is relatively stable. This is, however, not what happened to, for example, the planet Mars billions of years ago. Mars is smaller than the Earth, and it wasn't able to maintain its magnetic field, so then therefore its atmosphere was essentially at the mercy of the solar wind. And then slowly over time, billions of years, basically the solar wind, as it slammed into the Martian atmosphere, it stripped the Martian atmosphere away. So then therefore, we end up right now with a planet relatively close to us here at the Earth. It's basically more or less in the same place of the solar system as the Earth, so it's made out of the same materials, but it basically is an extremely cold, desiccated desert for this reason. So one of the nicknames for Mars, by the way, is that it's the Earth that failed. So that's an interesting way of talking about it. At any rate, however, the Earth is able to maintain its magnetic field for geophysical reasons that I'm not going to get into. It ultimately has to do with the Earth's size. So suffice it to say, the Earth's magnetic field protects us from the solar wind, and a good portion of the solar wind basically then gets deflected away from the Earth, like so, from F equals QV cross B. However, those particles that are relatively close to the Earth, well then as they slam into the magnetic field, I'm just going to draw a couple of them, some of those particles then do this. They spiral along the field lines, like so. And then notice what's happening here as I draw this. Those charged particles, when they're interacting with the Earth's magnetic field and spiral along the field lines, are directed towards the Earth's poles. So then therefore these charged particles slam into the Earth's atmosphere here near the Earth's North Pole, for example. And when this happens, some of the energy is released as light. That is the cause of the Aurora Borealis. The altitude at which that light is being emitted is in the neighborhood of about 60 miles or so above the ground. The same thing happens in the southern hemisphere as well, of course. So as these charged particles come in from the solar wind and then slam into the magnetic field, they get directed like so in this direction towards the Earth's South Pole. When those charged particles slam into the atmosphere at those locations, you once again end up with another aurora. However, in the southern hemisphere, it's referred to as the Aurora Australis. You don't hear about it that much, and the reason why is because there's not a lot of land in the southern hemisphere other than Antarctica that is close to the South Pole to be able to see it. So there's only some portions of very far South America that see it every now and then, or like very far southern Australia, like the island of Tasmania, which is off the southern coast of Australia. So you don't hear about the Aurora Australis all that much, but of course you hear about the Aurora Borealis a lot because there are a lot more people that live on land relatively close to the North Pole, northern Canada, Scandinavia, and so on. Okay, so that concludes this portion here of chapter 27. That concludes part 3 of today's lecture on magnetism. This is also the final lecture prior to spring break. Recall on Friday that it's Cesar Chavez Day, so no instruction will occur on that day, nor will there be any instruction over spring break. Make sure that you take a look at all of the screencast videos that I've posted for you in today's folder, and also the demonstration videos. And I also provided for you a nice link that shows some time-lapse of auroras. They're quite beautiful. I've seen them myself. They're very intense to take a look at. So make sure you take a look at that film. With regards to the global pandemic that is occurring right now, basically the peak of the curve is beginning to approach. The next couple of weeks are predicted to be quite bad worldwide and in the United States in particular. This is where social distancing becomes even more important than ever. So basically, hunker down for the next couple of weeks because unfortunately the world and the country in particular is in for a particularly rough ride. I wish you all very well. Today's shirt is Napalm Death.